if you have a point maybe hovering in the first octant, doesn't have to be in the first octant, but just for example, then this point can of course be described by an order triple XYZ, but you could also describe it using an R, which would be the length of this radius here to the value to the point in the XY plane you'd get by projecting the point in space straight down. And so that this angle here would be your theta. And then of course this height value here would be your Z. So the usual transformation equations apply. If you want x, you can take r cosine theta. If you want y, you can take r sine theta. Z is equal to itself, Z. R, if you want r for some reason, you could take x squared plus y squared. That's r squared, and then of course take the square root to get r. And then finally, the tangent of theta is equal to, well, y divided by x, right? So nothing new there. So it's polar, it really is polar coordinates in space. All right, guys, suppose I give you r is equal to 2 cosine theta. Now sometimes you have to use the brute force method, okay? The brute force method would be replacing r with the square root of x squared plus y squared. And then cosine of theta, I don't know. What would you replace that with? You'd have to work out the conversion equations and somehow replace that with something. But that's not the method you're going to want to use here. There's a trick that you were taught probably in pre-calculus, in trig if you took trig, and in calc 2 if you took calc 2. Does anybody remember what that trick is? I guarantee you've seen it, but hardly anybody remembers it. Yes! If I could give you a reward, I would. You multiply both sides by r. Why? Why does that help? Now, you're not squaring both sides. You're multiplying both sides by r. I'm going to put the r right there. Does everybody see why that helps? Because you get r squared, and then 2 times r cosine theta, direct conversions, right? R squared is x squared plus y squared. And of course, r cosine theta translates directly to x. It's beautiful. It won't always be that nice. Sometimes you just got to, you know, put in whatever translation you can, and it's going to come out ugly. But this one works out nice. It's a nice trick. Everybody should know it. Okay, if we complete the square on this thing, bring the 2x to the other side, and we get 0 on the right side. Complete the square on the x. How do I do that? What do I do? I take half the coefficient of the x, right? Since I already have a 1 in front of the x squared. Take half the coefficient of minus 2. What does that give me? Minus 1. And square that. That completes the square on x squared minus 2x, right? But then balancing it out, you have to add it to the other side as well. So what does x squared minus 2x plus 1 factor to be? X minus 1 squared plus y squared equals 1. Okay. And so what is this equation? In just the xy plane, what would this be? It'd be a circle. What would the center be? 1, 0. But it's in space. The z coordinate's missing, so if you translate a circle, a generating curve that's a circle, parallel to the z-axis, what do you create? A cylinder. And it will be a right circular cylinder. So this is a cylinder with axis through 1, 0, parallel to the z-axis. Okay. So how can we draw this thing? Right circular cylinders I like to draw first and then throw in the axes. It's just my preference. I can make it look a little better that way. Now, I could play with the view. And I think if I want to play with the view, I think I'd make this guy the z-axis. I can put 0, 0 anywhere. The cylinder goes on forever and ever, right? I'm going to put it so that the z-axis is right there, just because I think it looks good that way. But keep in mind, the cylinder keeps going down. I just cut it off there, just because I like the look of it. And then I could make this guy. Okay, if you think about it, what axis would that have to be? From this view. Well, okay, graph it. If you're not sure, graph it in the XY plane. Okay, 1, 0 is the center of this circle in the XY plane, right? So 1, 0 would be here. What's the radius of this circle? 1. So in the XY plane, wouldn't it look something like this? Would you buy that? Whoops. Does everybody buy that? So the way I've drawn it, what axis does this axis have to be? Have to be the x. And then going into the screen, I guess this would have to be positive y, wouldn't it? Everybody believe that? Okay. I haven't drawn it that way in a while, so I wanted to belabor that a little bit. Okay, so that this, what is this point right here? In space, what would this point be right here? It would correspond to this point right here. 2 zeros and then another 0 if you want to count the fact that we're in space, right? Okay, now we're talking this really is new. Spherical coordinates, a brand new coordinate system. So let me draw a picture so that this coordinate system makes sense to you. Let me draw just a picture of a point in space. Positive x-axis, positive y, positive z. So suppose we have this point in space. It's hovering over what would be the first quadrant, I guess, in the xy plane. So if you projected it down in the xy plane, it would land there if it went straight down. Okay, so how do there's another way to describe the position of this point in space. You could just take a direct distance from the origin to that point. So this distance from the origin right here on out, we call that rho. Row your boat, I guess. I don't know. Rho. So it looks like a P, but it's really a Greek letter rho. So rho stands for the distance from the origin to the point. And then we could steal the angle theta from polar coordinates or from cylindrical coordinates. So that would be the same as before. So theta would be this value. And then instead of using another distance value, we're going to use another angle value from the positive z-axis. We're going to call this other angle phi. And you measure from the positive z-axis so it comes out like this. You measure in that direction. And that angle right there is phi. So let me reorganize my row here to get it out of the way. So rho is a distance, and then phi is this angle right here. Okay? And those three values totally describe this point in red. And we use, now you have to be careful. Different books might reorder the angles because it really doesn't matter what order you write them in. But we're going to use the order rho. I think we use rho theta phi in this book. Yeah. But it really doesn't matter. Some books use rho phi theta. It doesn't matter. Rho theta phi is the one we're going to use. Okay? Now, it's important to realize then what r is, because it's going to help you translate between coordinates. Even though r doesn't appear here, it's going to help you to realize what it is. So if you were to create a congruent triangle to the one, do you guys see the triangle I've formed here? By dropping this perpendicular down, straight down, you form a right angle here. If you take the straight distance from the point to the z-axis, then you've got a congruent triangle, a congruent right triangle here. So that if this distance is r, so is this distance. From the point straight to the z-axis, that distance is also r. And using regular right triangle trigonometry, then you realize that r is equal to the hypotenuse, rho, times the sine of theta. Sine of phi, rather. Realizing that r equals rho sine of phi is very helpful when you write down some of these equations that can help you translate from one coordinate system to another. One thing I forgot to say, we're only going to let phi range between 0 and pi. And there's actually no reason to let theta get any bigger than 2 pi either. So we're going to let theta range between 0 and 2 pi. It's not necessary, it's just why go bigger than 2 pi, because then you've gone more than once around, right? Okay. And you can, believe it or not, describe any point in the universe that way. Okay, so there's lots of different conversion equations between coordinate systems. I'm going to write down 6 of them. These are the only 6 you need to know. The other ones are just bonus, if you remember them. So if you think about it, x could equal, x equals r cosine theta, right? But rho equals, I'm sorry, r equals rho sine of phi. So x, you could write down as rho sine phi cosine theta. And the way to remember that is r is rho sine phi. That's very helpful to know. And then, so if you want to translate from spherical, if you know rho, phi, and theta, you can translate to rectangular. You can get x. You can get y. Y is rho sine phi sine theta. That's the same thing as saying r sine theta. And it turns out if you use a little right triangle trigonometry on that picture that I drew above, you'll get that z is equal to rho cosine phi, actually. Okay, so again, that's rho right there. So 3 very important equations to know. Here's a fairly obvious one, hopefully. Rho squared is going to be equal to x squared plus y squared plus z squared, which is just the distance formula between the origin and the point in space, right? Tangent of theta is still y over x. That hasn't changed. And that's 5 of them, and the other one is kind of there implicitly, the fact that r is equal to rho sine phi. Okay, so these are the conversions you need to know. You take them as needed. I'll show you what I mean with some examples. Example, let's convert to spherical coordinates and identify the surface. X squared plus y squared minus 3z squared equals 0. Now you should be able to identify the surface without converting. What should it be? You have all 3 coordinates are squared and nothing else. No constant other than 0. Think about it. We'll come up with the answer in a second. Think about it, though. Okay, we're going to convert this to spherical. So it'd be nice if I had an x squared plus y squared plus z squared, right? Because that's just equal to rho squared if you look at this conversion right here. So there's a way we could do that. We could make it, just manipulate it algebraically. X squared plus y squared plus z squared. And then it is a cone, you're right, good. And then I wouldn't have minus 3z squared anymore. Wouldn't I have minus 4 of them? Everybody see that? Yeah. And so this part right here would be rho squared. Minus 4 times, okay, what related z and rho and possibly phi? Z equals rho cosine phi, doesn't it? Okay. So that would make, so z equals rho cosine phi. So if you plug that in, then we actually get rho squared minus 4 times, okay, rho squared cosine squared phi, right? You got to square both the rho and the cosine. Everybody see that? Now, I'm just going to factor out the rho squared. I want to figure out what this looks like. Rho squared, what's left if I factor out the rho squared? 1 minus 4 cosine squared phi. I've got a factorization. I'm going to set both of these factors equal to 0. And if I do that, I get rho squared equals 0, which means rho equals 0. It doesn't tell me a whole lot, does it? Or 1 minus 4 cosine squared phi equals 0. That tells me something. If I solve that for cosine, I'll get the square root of plus or minus the square root of 1/4. Everybody see that? Subtract 1, divide by negative 4, take the square root. So that means cosine of phi is equal to plus or minus 1/2, right? That means there's 2 different values. Cosine phi equals negative 1/2, or cosine phi equals positive 1/2. And you could actually take the cosine inverse and get a nice number here. What function, let's do this one with the positive. What acute value, what acute angle gives you 1/2 when you take the cosine of it? 60 degrees? Let's use radians here. So how about pi thirds? And then the cosine of phi equals negative pi thirds, or negative 1/2 rather. Well, okay. So you can treat the pi thirds like a reference angle. You know phi has to be between 0 and pi. So that means phi must be in the second quadrant to get the cosine of it to be negative. You know the reference angle is pi thirds. It must be 2 pi thirds. So phi could be 2 pi thirds. Oh, so it breaks down to understanding what kind of surface we get when phi is equal to a constant. So what kind of surface would that be? If phi is equal to a constant, rho is allowed to get as big or small as you'd like, and theta can keep going around. It would be a cone. In fact, this would be the top half of a cone. Where the angle phi is pi thirds, and this would be the bottom half. And if you think about it, in the original form of the equation, this is a cone. This is of the form we looked at. We usually had the thing involving z squared on the other side, but this is a cone. From those 6 quadric surfaces, we know that's the equation of a cone.